Hello and welcome. In this video, I'll be covering section 6.3, which is over the trigonometric functions of any angle. My goal for you by the end of the video is to be able to find angles that are coterminal with a given one, as well as finding complements and supplements, to be able to find the 6 trig function values of any angle in standard position, if you ever have the coordinates of a point on the terminal side being provided, as well as finding function values for any angle whose terminal side lies on an axis, and finding function values with angles that reference either a 30, a 45, or a 60 degree angle with the x-axis. And then the last part will be just reminding you how to utilize a calculator and potentially use that to come up with some angles in slightly different quadrants. Alright, so let's go ahead and start with just what makes an angle on our coordinate plane. So ultimately, all angles are just a union of two rays that share a common point, their starting point, happening to be called the vertex. So notice on our picture here, we've got our vertex centered at the origin. And then we have what are called the initial side and what are the terminal side, or what will be called the terminal side. So the initial side is always where our angle starts and where it should start. If we're in quote-unquote standard position, it should be the positive side, as you can see here, of the x-axis. And our terminal side is essentially wherever the angle ends or terminates. So as you can see here, the arrow is kind of pointing inside this angle from the initial side towards the terminal side. So this is implying that this would be something that went up to begin, which off to the right there's some examples of this, but that would make it a positive angle if I go up. If I were to go down to begin, as the third picture here is, notice that would be a negative. And that's going to transition ourselves as we kind of move forward. It's going to be something that we'll end up calling coterminal angles. Coterminal meaning that they share a terminal side. So to maybe just give an idea of what a coterminal angle would be, using the second picture, we have our positive version as it's being presented, but a negative version could also be drawn that, notice, start at the same and end at the same positions. However, it definitely would be a different size. If you look at that, that one definitely would be more than 180 degrees, whereas the one that was pictured was less than 180 degrees. In fact, if I made both angles positive and added them together, it should create one full rotation, which we hopefully know to be 360 degrees. But again, we'll explore that a little bit further here in this video. Just wanted to make the point with this one that we have those phrases, initial side, terminal side, and then where the angle actually exists is called the vertex. And if we go up from our initial side to start, that's going to be positive. If I go down from where that initial side is, it would be a negative value. And as we'll see, we are able to actually surpass a 360 degree angle if we were to go more than a full rotation around. Again, those things are going to be called coterminal angles that we'll explore here in a second. So a few more examples here, and kind of to dive a little further into that concept I just introduced. We have the idea of being able to represent multiple angles here, both positive and negative. The idea of having negative angles probably being somewhat new to you. But the measure of an angle potentially could be presented in degrees. We eventually will talk about how we can measure angles in radians, but for this specific section, everything should just remain in degrees. So if you have a calculator nearby, maybe just do a quick double check and make sure that it is in degree mode. Now what we can do if we have revolutions or rotations is recognize that one full rotation around is 360 degrees as represented on the far left here. Half a rotation then would be 180 degrees, and each of those technically we could say are coterminal. Key phrase there down near the bottom of the screen, coterminal, meaning it's just sharing the same initial and end or terminal side for that angle. So if we maybe use that second one as an example, 180 degrees, and notice it's positive because it goes up to begin, technically would be coterminal with negative 180 degrees if I were to have the same start but go down to begin to come up with that. Perhaps the final 3 or 4 versions here are a little bit better examples of that because they've already been drawn, where a positive 330 degree angle technically would share the same start and end as like a negative 30 degree angle. Again, all 4 of these here at the end, or the example I just added there to the second picture, those are all considered that coterminal idea. And notice that you can even have some angles that are even higher than 360, as like the 420 degree with 60 degrees is, or I can even have ones higher than that, 610 degrees, which is basically just a full revolution plus whatever that would be extra. Looks like it's almost 200 and what would that be, 50? Regardless, though, it doesn't really matter. We have a coterminal angle that could be negative. We have coterminal angles that could be positive. And basically the way that we would do that is just basically adding or subtracting multiples of 360 to be able to come up with that. So we'll explore just an example of how we can maybe come up with some positive terminal or coterminal angles as well as negative coterminal angles, and hopefully you'll find it to be a relatively easy concept. So speaking of that example, let's dive on in. So notice here it's giving us an angle 51 degrees. So if it helps, you can always like sketch a rough picture of what that would look like. So again, our start should be on the positive side of the x-axis, so it's going to be going up, and then once I get to what we would picture maybe as approximately 51 degrees, we could say, okay, that would be my angle. So if I needed to, as this problem asks for, if I needed to find two positive angles, I essentially would just start with my initial that they gave us, the 51 degrees, and just add as many 360s as I want. So I'm just going to find the next one by adding a single 360, which will give me 411 degrees. But I could technically also do, let's start there, but maybe add two 360s. And again, we can let calculators do a little bit of the computation here, or we could do that even recursively. If we think back to like a prior class, the word recursive just means use your previous answer. I could just add 360 to that 411 if I wanted to, and come up with the next one. So that would take me up to 771 degrees. Again, we could type it in as I have written there, or just continually add 360 over and over and over if we can do the mental math. Now as far as doing the two negative ones, I'll go ahead and do that in a slightly different color. The two negative angles here, if I were to do those, it would be start at 51, but instead of adding 360, I just need to take away some 360s until I get into the negative. So it really should just work out for this one being such a small angle that all I have to do is subtract one 360, and that should take me down into the negatives. So that would give me what, negative 309 degrees. And if I did maybe, let's start there at the beginning, but take away maybe two 360s, that would give me the next one. Or I could just subtract 360 from this 309, or negative 309, which takes me down to negative 669 degrees. And again, technically those are just like the first two that I would encounter, but I could actually continue this list on and on and on, meaning that these could be an infinitely long list of coterminal angles, so there's lots of different answers. But usually best practice, just come up with like whatever the next two positive ones would be, or whatever the first two negative ones would be, something along those lines, if they were presented in maybe a little bit larger form. So like instead of having 51 degrees, let's say it started as like, I don't know, 1,250. Obviously subtracting 360 would give us technically an angle that still would be positive, so that would be one of the first ones we could do, but we could also just add 360 and that would technically work as well. We could even be ridiculous with this specific question if I wanted to. I could say like an answer like 51 plus 20 times 360, whatever that resulted in on a calculator, that technically would still be considered one of the coterminal angles for the 51 degrees because it was some multiple of 360 away. And visually, to kind of give you an idea of why that's working, as if we look over here at the picture, it's basically just saying I'm starting at that and then going one full rotation around, and notice the position of that angle technically would not change. It would just be a larger amount of degrees that it must have taken to be able to actually get from start to finish. So hence again, it's not really changing the position of the angle, it's just giving us either a larger or smaller. Oftentimes what we'll want to do in this scenario is actually make angles smaller, not so much bigger, but just kind of showing how it can work and how we can make it turn into angles that are really giant or really tiny or even super negative. We have the ability to do that utilizing this coterminal process. Now, as far as some of the names of angles, hopefully this will be a little bit more just review than anything else. A lot of the names that you're hopefully familiar with are going to stay consistent even though we're talking about angles on a grid. We still have right angles being exactly 90 degrees. We still have acute angles being angles between 0 and 90. Obtuse angles, something that's greater than 90 but less than 180, and then a straight angle that's exactly 180. So really those are the only special names we're really going to encounter from time to time. We don't really need to worry about naming special ones that are larger, because we can technically utilize coterminal, or another word that we haven't talked about yet but called a reference angle, to simplify some of these things. So those four names again hopefully are just more review than anything else, but we also have a couple of other names of angles which are more pairs, not so much singular, and some of those we've already discussed prior in this class. A complementary pair of angles would be two angles that add up to 90 degrees. Do need to specifically be positive values in order to have either of these work as well. And then supplementary angles would be two positive ones that add up to 180. So the next slide here we'll practice just figuring out how to come up with a complement or a supplement, which again hopefully is as easy as doing the complementary, or sorry, not the complementary, but the coterminal process that we just discussed. All right, so the complement and supplement of this angle is the next example we'll work through. So 71.46 is our start. So the complement actually takes longer to write the words than actually to answer the question. All I have to do is just figure out what adds up to 90 with that. So the easiest way to accomplish that would just be start at 90 and take away the angle I know, and that should give me the angle that's left. So in this case, that would give us 18.54 degrees as its complement. As far as its supplement is concerned, if I could actually spell supplement, sorry about that. So supplements is, instead of adding up to 90, it needs to add up to 180 this time. So just like we did with a complement, we'll start with the value we want to add to, which is 180, take away the value I know, which is 71.46 as provided, and then when I subtract, that would give me, it looks like in this case, 108.54. So again, finding complements, just adding up to 90, finding a supplement, adding up to 180. Relatively straightforward. If this was presented somehow, some way in like a degrees, minutes, seconds, I'd recommend just converting it to decimal as this one was already presented as, and then we can do the add or subtract values a little bit easier without having to worry about like how many minutes or seconds that happens to turn into. But it shouldn't happen very often. Just wanted to at least point out, if you do have degrees, minutes, seconds, immediately just convert to decimal, and that should make the rest of the problem a little bit easier. All right, so moving on to the next main topic. Now we'll talk about how we can figure out trigonometric functions of any angle that happens to be in this standard position. Now what we can take advantage of, as you can see with the picture here in the middle, is we can draw these things called reference triangles, where if I ever do want to draw a reference triangle, what's key and what's super important is this right angle always needs to be with the x-axis. So just try and commit that to memory, that if you're going to try and draw one of these reference triangles, that the right angle is at the x-axis. Super important for this, because what we're going to utilize here is we're going to start utilizing more of the ordered pair at the end. So this x comma y, as you can see on the picture, as like part of the key things for my ratio. Notice on this small triangle here, we've got now the opposite side technically is the y value in reference to the angle. The adjacent side is the x, and then the hypotenuse each time is just whatever the r is. And since we're having our vertex at the origin, really kind of utilizing that letter r representing radius, notice it kind of creates this idea of a circle, hence why we have this equation x squared plus y squared equaling r squared that will be a little bit more important. Keep in mind from our past, that would be an equation of a circle centered at the origin, specifically with a radius that would match whatever the r value is. So in this scenario, notice we can come up with our sine, cosine, and tangent utilizing SOHCAHTOA if we needed to, but really what we should try and set a goal for is getting the fact that sine is going to connect with the letter y, cosine will connect with the letter x or the value of x, and then tangent is actually a combination of the two. And really what tangent is kind of a shortcut, or something that we'll explore if you continue on this calculus path that some of you are on. That technically turns into a concept that we'll explore a lot more in a calculus level class, which is called slope. But slope is something that we've been dealing with for years and years and years. Keep in mind that's just rise over run, and hopefully you remember that rise goes with the letter y, whereas run goes with the letter x. So even if you just remember tangent and slope going hand in hand, that should help remind you that the y value goes on top and the x value goes on bottom. The other ones, notice it just has the r, or whatever the radius is, as the denominator, and that's again because I'm utilizing the SOHCAHTOA relationship we've explored earlier in this class. Now, as far as the reciprocal functions are concerned, right, secant, cosecant, and cotangent, those specific ones, all I'd have to do is just flip whatever its corresponding ratio is to be able to come up with it. What gets a little tricky with this one is, what if I had a point that was not out in one of the quadrants as this is, which as just a quick little review while I'm thinking about it. Let's go ahead and talk about how the quadrants are numbered, just in case we don't know. So just like we would go through positive angles, we would start with the positive side of the x-axis over here, and as I go around, it would just be numbered in the order that I meet them. So this, as I go up to begin, that would be the first quadrant I'm in, hence why we call that the first quadrant. As I continue around, again going in a positive direction, that would take me over to this far top left one, which would be our second quadrant. Dropping and continuing on around, it would be our third quadrant next that we would encounter, and then the last one is the bottom right. So again, that's just the idea of kind of going around in that order as a positive angle. That's how the quadrants have been numbered. And oftentimes we use Roman numerals to do that, but you could also do things like Q1, Q2, Q3, or Q4 to represent the fact that you're talking about a quadrant. So, anywho, if we go ahead and look at what we got here, notice by having that right angle always with the x-axis, that will always make the opposite the y, the adjacent the x, and the r as the hypotenuse, which then allows for sine to be connected or to the y, or the cosine to be connected to the x. So again, that's trying to stress the importance of making sure that your right angle is always with the x-axis. Never, ever, ever draw a triangle going to the y-axis. That really will not be something that will help out. In fact, it will actually create more problems for you than, I guess, positive things. So let's go ahead and try an example, and I'll probably make up another one here before this one ends, of just something that I know will pop up in your homework. That has this idea of this reference triangle being drawn already for us, but notice it's given us an ordered pair, so I at least have an x and a y. So I could solve for what this r is just by utilizing what we know. So r squared, according to the equation of a circle, should equal the x squared plus y squared. So for this one, my r, if you really wanted to, it's just going to be the square root of, and let's go ahead and just put those numbers in. So it'd be -4 squared added with -3 squared. And if I go ahead and square those two numbers and add them together, that would be a 16 plus a 9, which is 25. And the square root of 25 would equal 5. So I know that this hypotenuse, or this r value, is in fact equivalent to a 5. So at this point, we should be able to come up with any and all trig ratios we might want. So let's just start with the three basic ones. The name of the angle over here, it looks like it's theta, so I'm going to go ahead and use that same notation. So sine of theta will equal, and then it would be the y value divided by the r. So we've got our y value to be -3. We've got our r to be 5, so -3/5. While we're doing it, let's just go ahead and figure out what's the cosecant, since it's just the reciprocal. So cosecant of theta, all I'd have to do is flip that ratio, and it would become a -5/3. So notice the negative doesn't change at all. In fact, I don't really have to keep the negative attached to the 3. I just need to have the negative somewhere. So I personally kind of like having the negatives in front if I'm thinking ahead. So going back, I could have said that that was just a -3 in front of, or sorry, a negative sign in front of 3/5. But again, you could have the negative on the 3, you could have the negative on the 5, or you could have it out front, kind of like I have with that second. If we go on to the next one, let's say we do cosine. This one would be our x value over the r. So again, kind of just making that connection of cosine with x, sine with y. That will pay off moving forward, just the quicker we can connect those things. Here it looks like I'm going to have a -4 as my x value, so -4 over that 5, which was the r. So since we've got that one, may as well just do its reciprocal secant. So let's say secant here now would just be that fraction flipped, so -5/4. And then the last one we need to figure out, or last pair we need to figure out, are the tangent and cotangent. If tangent here is the y divided by the x, here that would give me a -3 over a -4, which the two negatives I could technically have probably seen were going to cancel each other out, so I just get +3/4, which then means cotangent would just be the flip version of that, so that would be 4/3. Now just to, again, I kind of preface this at the beginning of this slide, but what if, here's the situation that would pop up on your homework assignment, what if I have one of the points that actually falls on a quadrant itself? So let's say hypothetically we have this point down here, which would be like, I don't know, let's call it 0, It'd have to be a negative number, so let's do like maybe -3, just for the heck of it. So notice at this point, like my angle technically would be like all the way around here, so that really would be like 270 degrees if we wanted to think in terms of like that would be 390s away from wherever I started. We could also technically call this -90 degrees if we wanted to utilize a negative angle. But regardless, let's say I just wanted to figure out what's the sine of 270, cosine of 270, and tangent. Let's do the main three. If we go through and do those things, notice our x value here is a 0. And being able to find what the r is, if we really think about it, well, the r is just the how far out it goes. And our radius should always come back a positive value. So this is more of a, not so much the directed distance, it's just what is the distance. So for this one, it would just be, it's a distance of 3, and now come up with the exact same approach that we had before. I've got the 3 numbers I need. I have the x, I have the y, I have the r. However, as we'll see here in a second, the fact that 0 is a part of this can get a little bit weird. So if I did the sine should be the y divided by the r. So that would just be a -3 divided by 3, which actually does reduce to a -1. If we go with the cosine, this would actually give me 0 over the radius 3, and 0 divided by anything stays 0. So that wasn't super tricky yet, but if we look at the next one, now it's going to be the y divided by the r, or sorry, not the r, but the x, to come up with tangent. So that would be -3 divided by 0, and this is now where that issue pops up, right? Division by 0 has always been a no-no. So if we ever have that happen, what we need to make sure of is we just need to connect that with the idea of that word that we need to remember is undefined. So tangent of 270 degrees, we would just say, is an undefined value. Now, what's even more tricky with this is we would, let's say we needed to do the other 3, secant, cosecant, and cotangent, it would just be flipped versions of those. And so then the question becomes, well, how the heck do I flip undefined? Well, that's where we just need to kind of think, what does it really mean to be undefined? If it's undefined, that means 0 is on the bottom. So when I flip it, now 0 would be on the top. And when 0 is on the top, like it was for cosine here, 0 on the top actually is 0 still. So kind of the key takeaway here that I'm trying to make a point of is if you ever need to find a reciprocal of either 0 or undefined, they are actually going to turn into each other. So like 0 flipped, in other words, would become undefined, or undefined, quote unquote, flipped, would become 0. So those two are going to be the reciprocals of one another. What's kind of easy with 1 or -1 in this case is if I flip it, it just stays a -1. Or if it was +1, it would stay +1. But again, just wanted to at least kind of point that out because it does pop up from time to time. It's not super common. And in fact, we'll learn next section a little bit maybe easier way to know how to do angles such as like this 270 degree one. But for this assignment, just to make sure that you're aware of it, that would be the way that we would approach it. Just realize when we have division by 0, the key word here is undefined as our final answer. It's not something like no solution or anything like that. Now the next example, notice this one doesn't provide a visual like the last one did, so what we could do is just kind of force that visual to happen. It does give me at least one ratio. It gives me that tangent is -2/3, so that's going to be a y over an x. The tricky part there though is I don't know which out of those two that negative is going to go to, whether it's going to go to the 2 or the 3. That's where the second half of this part, where it says second quadrant, that's going to be key. So that means it should be over here in the second quadrant. So if I just go ahead and just do a quick little sketch of a triangle where it forces that 90-degree angle to be with the x-axis, I've got now my reference angle that I can utilize for this, but technically the angle we're talking about is on the outside. We'll talk about the why that technically works here in a second, but again, we just want to focus our attention on the angle that actually would be at the origin for that right triangle is going to be key. Now, because that's in the second quadrant, and I also know that my ratio for tangent is somehow -2/3, I know that the y value is going to be a 2, I know the x value is going to be a 3, so now the question just is, well, if I'm in that quadrant, which of those two numbers should have the negative? Well, the 2 is going up, and in going up, that should stay positive, but the 3 is actually going left. So since it's going left of that y-axis, it's actually the 3 that for sure has that negative sign. And then we can come up with our r the same way that we did before, so I'll just go ahead and do that maybe underneath here, where it would just be r equaling the square root of those two numbers squared and added together. So 2 squared plus -3 squared. Add those together, I get 4 plus 9, which would be 13, so square root of 13 is our radius. So now going through and identifying each of the key things, I would do sine of theta should equal the y value 2 over the r I just found, rad 13, and then rationalize. So that should turn into 2 square root 13 over 13. And while I'm doing it, let's get cosecant out of the way as well. And it's actually easier to flip the original version, so that would just be square root of 13 over 2. Next one I can do is cosine. So cosine here, let's go ahead and get out of the way. That would be the x value, negative 3 over the square root of 13, which again I can rationalize just by multiplying top and bottom by that square root of 13. And since I've got that one, I should be able to do the secant as well, where it's just flip one of those two versions. I think the first one is easier to flip because it moves the radical already to the top. So negative square root of 13 over 3. Last pair I've got, tangent of theta. That's going to be the one that was actually provided, so negative 2/3. So cotangent would just be that flipped, negative 3/2. Okay, moving on to the next topic, which I've somewhat referenced earlier in this, which was called a reference angle. This is essentially just an angle that is acute, always formed with the x-axis. So key parts again, reference angle is the name, and specifically is an acute angle where the terminal side makes the angle with the x-axis. So as you can see with the bottom picture here, the angle that we would be talking about would be this 150, but the reference angle it has is the how much extra, or the what it would take to be able to get to 180, since that's the left side of the x-axis. So in this case, adding 30 would take me up to that, so that would be a 30-degree angle on the outside of that angle. And what we do is we use that reference to allow ourselves to kind of see this right triangle here. If we do a quick little recap of a 30-60-90 as well as a 45-45-90, those specific special right triangles are things that pop up quite often, at least with some of the angles that we'll be discussing. So if we go ahead and just talk about that 30-60-90 triangle, we've got 30 degrees, and that bottom left, we'll go ahead and call this one the 60-degree angle at the top right. And when it comes to labeling this, we always start with the what's across from the 30, or the short leg in this case being a 1. The hypotenuse is always double that, and then the longer leg, or the one that's across from the 60 degree, is always whatever the short leg is times the square root of 3, so 1 times square root of 3 would stay that. And once I have all three of those sides labeled, it should be something that I can now utilize, either thinking back to SOHCAHTOA, or just remembering as we draw the triangle how to label the sides. Just realize that now we potentially could have some negatives once we go into other quadrants. So paying attention to whether the x or the y would be, I guess, my rad 3 or my 1, kind of depends on if it's a 30-degree angle or a 60-degree angle. But also paying attention to the direction will help us identify whether we need to put a positive or a negative value on it. If we think about the 45-45-90, I'll do that off to the right here. So 45-45, that's the right isosceles triangle, where the two angles are the same, which means the two legs must be the same. And one possible version of this that I think is probably the easiest to remember is just if I make the two legs equal to 1, the hypotenuse is whatever that length is times the square root of 2, and 1 times the square root of 2 would just stay square root of 2. So again, being able to recall those two triangles, where the 30-60-90, technically I need to worry about two different orientations of it, one for the 30-degree angle, one for the 60-degree angle. But as long as I can recall those and at least draw a reasonable sketch in each quadrant, should allow me to, I guess, deal with answering potential questions such as like what's the sine of 150 degrees, or cosine, or tangent, or any of those other ratios. So as you can see with this example, if I said what is the sine of 30 degrees, sine of 150 degrees, I would use this 30-degree reference over here inside that and go what's opposite, that's 1, what's hypotenuse, it's 2, so this would just be 1/2 is the equivalent to the sine of that 150. Alright, so let's actually do some examples where we see it instead of just talk through it like I did with that 150 there. So here we got a couple of examples, angles that we probably right at this moment don't know all of the ratios for. Here it just wants us to do the sine, cosine, and tangent, so it's not like we have to do all 6, we just need the probably the three that we're most comfortable with anyway. So coming up with those, we would just need to maybe start by just picturing where is that angle. So 225, if we start it in standard position, I'd start at 0, it's positive, so I'd go up and I'd just kind of figure out how far it would take to get to 225. So I've gone 90, now I've gone 180, so I need to keep going a little bit more. So it seems to me like it would probably be somewhere in that range, because down here this would be like 270, whereas off to the left it's 180. So it definitely falls somewhere in the middle of that. So if we think about the how much was that, well, I've got up to 90, I got to 180, and then I needed to go how much further, because that's really the reference angle that I need to worry about. Well, how much further would I go from 180 to get to 225? Well, that would be 45 more degrees. The other way we could do it is just do 225 minus 180, and that would have given us that angle as well. So with that being said, we can maybe draw a little bit more reasonable picture here, where again it's that same angle, but this time just focus my attention on that right triangle that it forms. Well, since this is a 45-degree angle, this is going to utilize that 45, 45, 90, which we just said were a 1, and a rad 2 as far as the two legs and the hypotenuse. However, based on location, since I'm going to the left and I'm going down, those two values actually both would need to be negative. So at this point, now that I have that triangle that I can reference here off to the bottom, or at least the bottom left here, I should now be able to figure out what sine, cosine, and tangent of each of those are. So sine of 225 degrees looks like it would be the y value, which is -1, over the r, which would be square root of 2, and then rationalize, and I get a negative square root of 2 over a 2. Similarly with cosine, since it's the same side length, I'm just technically referencing the x, but the x being -1 is why this isn't going to change a whole lot. It'd be -1 over the square root of 2 as well, which again gives me a square root of 2 over 2 with a negative in front of it, just like we got with the sine. So the sine and cosine of this specific angle actually have the exact same ratio. The tangent ratio actually is the easiest of the three here, because we don't have to do any rationalizing. It's just the y value, which is -1, divided by the x value, which also is -1, and two negative ones when I divide them give me actually a +1. So as you can see there, the use of that 45, 45, 90 triangle technically is allowing me to answer what the ratios for this larger angle, 225, would be. And notice again, just because it was larger than 45, it actually was outside of the first quadrant, I just then had to start worrying about potentially some negative signs, which both our sine and cosine came back negative. Now the next one, we'll do pretty much the same approach. This time though it's a negative angle, so when it comes to sketching our angle, instead of going up to start, we're going to go down. So again, starting at the x-axis, I'm just going to go one time around, so that would be 360, so I obviously haven't made it to 780 yet. Another time around, that takes me up to 720, so if I'm at 720, it looks like I just need 60 more degrees to get to 780, so that would take me to right about there. So this is giving me a 60-degree reference angle. So if I maybe just draw it all on the same shape here, it looks like we'd end up having, actually I'll just separate it because that's kind of, I don't know, a little clustered there. So again, my angle would be right here. It's a 60-degree angle there at the origin, so that's my reference. And it looks like my short leg then is actually the one that's across from this 30 down here, so that's where the 1 will go. I know the hypotenuse again should be a 2 for this specific triangle, and then a square root of 3, but because it's actually going down that amount, I'm going to go ahead and throw a negative on it because the y value in this case should be negative. My x value on the other hand, since I'm going to the right, stays a +1. And just like we did before, we're now going to go ahead and do the sine, cosine, and tangent of this, but again, even though we're using the 60-degree angle as the reference, we're technically finding the sine, cosine, and tangent of this -780 degrees. So if we start with the sine, that looks like it's the negative square root of 3 over the r, which was 2, so negative square root of 3 over 2. Radical is in the top, so I don't have to do any rationalizing. Next one, cosine of -780. That's going to give me, it looks like an x over r is 1 over 2. And then the last part, tangent of -780, would be that y value negative square root of 3 over a 1, which I could technically just say is negative square root of 3. Alright, moving on to our last example, which is more going to be how do I deal with utilizing a calculator where our calculator maybe doesn't necessarily give us the angle we truly want, and that's more because of a restriction on the function that I'll need to use to cancel either a sine or a cosine or a tangent or any other one. But those are our three main ones that our calculator has. So that's really what these two examples will be, or these two parts for this example will be. So let's go ahead and start with the first one. It wants us to figure out what is the angle if we know that the sine of the angle is 0.2812. And specifically for this one, it's wanting the angle to fall between 90 and 180. So we can maybe kind of picture over here, like 90 is this top part, 180 is over here. So it's supposed to somehow get into quadrant 2. So let's just see if maybe when I type it in the calculator, it already ends up there. The way that I would do that, keep in mind again, to cancel sine, I'm going to have to use its inverse. So for this one, theta would just be equivalent to the inverse of sine. So arc sine is its name of that ratio 0.2812. If I go ahead and jump over to the calculator really quick, we end up getting this value, if we type it in, arc sine of 0.2812, I believe was the number, and we get 16.33 degrees. So if we switch back, we can say, okay, that on the calculator said it was 16.33 degrees, which we could, if we approximate, would be positive 16, so maybe a kind of small angle like right about there. Now obviously when I draw that angle, it's not quite in the quadrant we want, but since we're talking sine, remember from earlier goes with the y value, I just need to think like, okay, if this is my ordered pair right here at the end of an x comma y, I just need the y value to stay the same. So if I need the y value to stay the same, it would just kind of be like, let's just reflect it maybe over here. That gets me pretty much a mirror image angle over here, where now the 16.33 is that amount of space. But the angle I actually want is the one from standard position that gets to that terminal side. So as you can see here, it's definitely going to be larger than 90 degrees, but less than 180 as I've drawn that yellow one. But how would I come up with it? Well, ultimately, if we know that that amount of space, if that's theta, if I add 16.33 to it, that technically would take me up to 180 as we see here. So kind of the easy way to come up with that would just be, let's just figure out what that space is by doing 180 take away the 16.33 that I know. And if we go ahead and do that, that should give me, let's see, let's type it in, 180 minus the 16.33, and we get a value of 163.67. Notice again, that now falls inside the window we were looking for. It is greater than 90, and it's also less than 180. So on occasion, again, your calculator will just give you an acute angle, especially when you're using either arcsine or arctangent, which we'll explore more the why that happens. But here, we more just need to be able to recognize, like, if it gives me an answer, but it's not an angle that's in the correct spot, we just need to kind of find a way to either reflect or maybe rotate, and just figure out how that space would be. So if I needed to be like in the third quadrant, for example, I might just reflect it across the origin and have my 16.33 be with that x-axis again in that area. Now this one, obviously, that wouldn't make a lot of sense because it was a positive ratio and positive y value should stay above. But for this one, again, that kind of concept would be something where it's just think how much space would I need, and should I add 180, should I subtract 180, should I add to 180 or subtract from 180? Or if I get into the fourth quadrant, I might start thinking about 360 over here on the right side. So anyway, let's go ahead and look at maybe the next example, see if this one helps make it make sense. If we need some more examples, just let me know. The tricky part of this one is what's giving us the cotangent, which we don't really have a button for. So what we'll need to do right off the bat is switch it to tangent. And the easiest way to do that is just take the ratio and put it under a 1, because that's what's accomplishing the flip or the reciprocal portion of it. And if I now try and cancel the tangent, it would just be utilizing its inverse. So arctangent of this ratio, -1 over 0.1611. And if we go ahead and flip back to the calculator, type that in, arctangent of 1 divided by -0.1611 gives me a value of -80.85-ish. I probably should have pointed out before I started this where we needed to be. So it did say the instructions are the theta should fall somewhere between 270 and 360. So sketching a little picture, 270 would be down here at the bottom, 360 is off to the right. It's technically in the same spot as 0, which hopefully makes sense. But if we now think in terms of what would negative 80.85 look like, well, negative 80.85 would technically be starting on the positive side of the x-axis, but this time going down because it's a negative. And it doesn't quite make it to 90, so it would be something approximately like the angle I just drew there. But as we can see, that is in the right spot. It's just not between the right two numbers. So this is where from earlier we talked about coterminal angles. All we would do is just think about, okay, if that's the angle, if I don't want to move it, I'll just add a full rotation the other way. So if I just added 360 to this number, that should take me up to the angle I need. So if we flip back, we've already got the answer on our screen. Let's just add 360 to it, and notice it gives us our answer now of 279.15. So 279.15 degrees, which now does fall between that 270 and 360 we were aiming for. So at that point, we've got the angle locked in where it needed to be, as well as inside the range that we wanted. Now, had this wanted it to be, for example, maybe in the second quadrant, instead of doing a plus 360, we actually would maybe have just thought of like adding half a rotation, so maybe adding 180. Should I have needed it to be like between, say, 90 and 180, there would be a way that I could accomplish that. And again, we can work through more examples if that still isn't quite making sense. I think as you see it and work through it, the logic of it will start to kind of come together. Hopefully it's come together with just how I've explained it so far, but again, if you have further questions, just let me know. Anywho, hopefully this video has been helpful for those that maybe were struggling with the section. So if you, again, still have further questions, come find me and give me a chance to help. Regardless, I appreciate you taking the time watching the video, and we'll catch you next time.